So the rest of the morning is going to be mostly me talking at you with some interjections by the other two, giving you an overview of electron microscopy, specifically scanning electron microscopy. This will get us all the terms down. This will get us how everything works down. When I was taught how to use an SEM, it was mostly just a black box. It was, here's how this gets an image. Here's the settings used, and I didn't know what the heck I was doing or why I was doing those settings. So this session and a few of the others are aimed at making sure you know what is happening underneath, so that when you're changing a setting, you actually know what setting it is you're changing for in a classroom context, and then you get to actually change those settings later. Okay? Don't hesitate to ask questions, throw things at me or anything else if you need to while I'm up here doing this. Okay. So, you and I can see things down to a certain scale. That tends to be down to 10 to 100 micrometers, something like that. We can't really see bacteria with the human eye. You can get down to a human hair, a little bit of dust, something like that. The next size down, light microscope, can get down to, sub-micrometer-ish stuff. You can see bacteria. You can see little bits of dust in a rock. If you want to get stuff that's smaller than that, an electron microscope becomes the main option to do that. Electron microscopy heads back to the early part of the 20th century. The first published design for an electromagnetic lens goes back to 1926. You may notice the German companies showing up on here. That is not a coincidence. This was coming out of the universities and industries in Germany in the early part of the 20th century. The first working prototype of a transmission electron microscope was constructed in 1931. It is shown there at the right. This magnified a metallic grid by a factor of 17. 2 years later, they had a design that could magnify things from 17 up to 12,000. They partnered with Siemens to develop the design in 1937, and this work eventually led to one of the 1986 Nobel Prizes. I believe that was probably physics, but I have to double check which one. Since these were German companies in the 1930s, you will also note that Siemens has acknowledged their contributions to, and apologized for their contributions to the German government in the 1930s and 1940s, because that's how that part of the century went. Transmission electron microscopy is in some ways similar or simpler than scanning electron microscopy. In a transmission electron microscope, you just blast things through a sample. Scanning electron microscopy is a different setup. It is more closely related to electron microprobes, in that both of them are sending beams of electrons at a sample, focusing on the sample rather than blasting through, and using the interaction between the sample and the beam to give a signal. The electron microprobe design was first in a PhD thesis in 1951. Scanning electron microscopy started in the early 1960s with the development of electron detectors. So in transmission electron microscopy, we just blast a signal through our sample and collect anything that's on the other side. For scanning electron microscopy, we're going to need to develop detectors that can pick out specific energies of electrons at certain spots and turn those into images. Scanning electron microscopy was first put out by Cambridge Instruments in 1964. They thought this was going to be a niche instrument, and it most certainly was not. By 1968, they had built 150 electron microprobes and over 500 scanning electron microscopes. So this took off rather rapidly, and 1968 is, of course, the moon landing time, so the labs are gearing up for doing samples like that. The scanning electron microscope compared to optical microscopy or transmission electron microscopy has a number of specific uses and advantages. You can magnify things to a greater degree than an optical microscope. In a good scanning electron microscope, you can get sub-micrometer resolution, and that can allow you to pick up details that are not visible in any other technique. You get two other big advantages. A TEM, you pretty much have a very thin sample and you blast electrons through your thin sample, where you're somehow taking advantage of the fact that your sample is thin enough to transmit stuff. In a scanning electron microscope, you do not have to make things super thin. If I had to make this super thin, I would not see that this structure was coiled. Scanning electron microscopy can remain in focus across some fairly substantial distance. So you're seeing structure here that is popping out across a range. It's not just focused on a single plane. That we would refer to as a cough, as depth of field. While we're doing this, we also get information that's not just an image of the feature. There are details that can be turned into compositional information in several different ways, all of which we'll go through during the week. When we speak specifically of modern electron microscopy, we're going to see that there's kind of two breakdowns of this right now. That the way that engineers are taking this, there is the ultra fancy designs that get put in their own dedicated room, often climate controlled, often sound controlled, to make sure that nothing vibrates in the room. And desktop SEMs, which is technically what we have in this building and what you'll be working with here. This is kind of the looks of a field emission electron microscope setup. Note the sound dampening on the wall. That is the look of a desktop microscope like the one you'll be working with in this course. Each of these has their own advantages, and they can be designed for a number of different purposes. The big ones, the field emission or floor model SEMs, they will get you the highest quality imaging and analysis that you can get. They are able to image things more finely than most desktop SEMs. You'd be surprised how good the desktop ones can do, but these can get you better resolution. If you have a whole room that's built for the thing, you can also develop specialized applications that are not easy to do on a small unit. This could be focused ion beam sample preparation, cathodoluminescence, a cold trap to keep or things that are degassing in there from getting out, a technique called EBSD, electron backscatter diffraction. That is a very cool one. We'll talk about that later. You can fit bigger things in those. Sometimes you actually want an SEM image of something that is big enough you don't want to break it down. And it may be more easy to do if hypothetically our Titan person was actively drying their sample out in the SEM, that might be something they could monitor more easily in a system like this. The desktop or tabletop ones, on the other hand, they are about an order of magnitude cheaper. So the ones on the left might cost a factor of 10 more, depending on exactly how you have it built. These are relatively affordable. These can be afforded by an average lab that is doing something as part of a single research project. The sample preparation and settings are often easier to work with. They are built so that students can figure out how to use them rapidly. It may not require a full-time manager. The one on the left, you're going to need a full-time manager to make sure what happens when that one breaks. You can fit these anywhere, including in small rooms in the corner of the Lunar and Planetary Institute. You don't necessarily need a dedicated additional power supply. You don't need to build an additional transformer. You can literally plug them into the wall. They are often even portable. It is actually possible to take these out in the field with you. There was when one of the initial eruptions in Iceland happened a couple of years ago, one of the teams up there was literally using the same electron microscope that, well, not this, the same model of electron microscope, not the same microscope itself, literally plugged in a tent, run off of a generator. So, you know, literally out in the field, you can pull a sample off a lava flow and put it into an electron microscope in minutes after it cools to get it in there for analysis. So each of them is useful in their own way. Each of them has their pluses and minuses. Here are the details behind ours. If there's a term on here you don't know what it is yet, cool. Then it's my job to have you know that by the time we finish this morning. Okay? This one was purchased in 2020 with a strategic investment grant from our parent organization, USRA, supported by NASA as a planetary science enabling facility in 2022. It offers secondary electron, backscattered electron, and EDS analysis. We also have an evaporative carbon coater funded by the PSEF grant. It is typically used by LPI staff, postdocs, and interns. Roughly 50% of its time is available for visiting scientists and outside users. Should you actually want to come back and use this facility, it is currently available with no cost. So if you're ever in the area and you need an electron microscope, let us know. Tip of tea. This is the Wikipedia version of a scanning electron microscope with the main ingredients that we're going to need. How do we make an electron microscope work? We need a thing to hold the sample at the bottom. We need a way to focus the electron beam on that sample. And we need a way to generate an electron beam that can travel from the source of the electrons to the sample itself. And then we need something built in to detect the electrons or X-rays or whatever else it is that we generate as we go through. Most electron microscopes, in fact, all of them, will have some version of a vertical column. The top of that will be an electron gun that generates an electron beam. Those electrons will get accelerated and focused through a series of lenses onto the sample. And then down at the bottom, where the sample is, you'll have a series of detectors. That's in both the desktop ones and the fancy room-sized ones. Now, we're going to go through the details of how many of these systems work at an overview level. There's obviously going to be stuff that I won't cover completely. We may get back to some of that later in the week. We may not. Where do you generate your electrons from? There are three types of electron sources used in electron microscopes and also electron microprobes. I will mention those occasionally and eventually have a good understanding of how they're different. Tungsten filaments, lanthanum or cerium boron or boride, I guess, crystals, and field emission guns. The first one of these that showed up in the electron microscope was a tungsten filament. The first ones from the 1960s were tungsten. You apply a small voltage across this little filament. It heats up due to resistance. That generates a cloud of electrons at the tip. And then you put a positive charge somewhere to accelerate the electrons away from that tip. And now you have generated electrons and are firing them off in the direction you're accelerating. These are perhaps the most common type of electron gun. They have been in operation since the 1960s, I believe. They are relatively cheap. And it's relatively easy to replace them. When one burns out, you just pop it out of you build the device so that these are accessible. You can pop them out and replace them. They themselves do not have to be put at an ultra high vacuum to operate. They need a vacuum, but it does not have to be a super high vacuum compared to what we'll talk about in 2 minutes. The electron microscope in this building has a cerium bromide source, which is, rather than a tungsten filament, it is a crystal of a rare earth element bromide that, again, is heated, and that generates an electron signal that you can accelerate from the tip into your gun. So when you're using the electron microscope here, you are relying on a cerium boride, single crystal, to generate the electron beam. Those electrons get accelerated downwards. There are some advantages of this. Compared to a tungsten filament, your electron flux is something like 10 times higher. So you can get a higher beam current out of this, leading to higher brightness. You also, compared to your average tungsten filament, get the electrons from a smaller spot, which allows better focusing of the electrons. You get a more narrow spread of energies, so your energies of your electrons are better controlled. And the lifetime of the filaments is roughly 10 times as long, which is a nice thing because getting into the microscope and actually replacing this part is more complicated than doing so on a tungsten filament. It requires a better vacuum to operate. It's more expensive, and it can take a while for these to heat up. Tungsten filaments heat up a little more quickly than these and reach saturation where they're just fluxing electrons off of them at a more reasonable rate. The most fancy and most complicated ones are called field emission electron microscopes. So if you ever walk to an electron microscope on your campus and it's the big whole room one, and it's labeled as an FE SEM, this is what the FE stands for. It is telling you that it is a field emission gun. This is tungsten again, but it is not a single filament. It is a tip like that. So you're looking at, and this is actually ironic, this is an electron microscope image of an electron microscope tip. You like that? The microscope inception. Okay. You, at high vacuum, apply a voltage to this tip rather than heating it. And the accelerating voltage causes electricity to be drawn off of and emit from this tip. So it's emitting as a field rather than as a thermal emission, is the origin of that term. All right. Advantages of this compared to a tungsten filament, oh, you might have a factor of 1,000 more electrons, which is kind of useful because now you have a much stronger beam. You have a narrow focus point, a very tight distribution of electron energies, and the lifespan of these is particularly long enough that I don't have a good number to give you because hopefully this is the kind of thing you're not replacing very often at all during the entire lifespan of the electron microscope. The disadvantage here is cost. You have to have a very high quality vacuum for this to work because otherwise you will not get the electron emission that you want. And we have some current issues, but this is the difference between this design and this design is that difference between $200,000 and $2 million for a facility. So that is our method to generate electrons. We start off up here with one of those three types of electron guns. We apply a voltage to draw off the electrons, and that sends them down our column. Well, now we need to control those electrons to send them to a single spot on our sample and to quote unquote scan across the pattern, across the sample in a consistent pattern. So that to make this a scanning electron microscope, we need to be able to scan. That is done with a series of lenses, which are electromagnetic lenses rather than glass lenses. They are basically controlled magnetic fields. They control the direction of the electron beam. They focus the electron beam. And when you're in scanning electron microscopy, it will move the beam across the sample in an organized pattern so that you can take an image of the area that you're focusing on. How do the lenses work? Well, all right, a little bit of in the details here. It's basically a coiled wire where as you send your electrons through, you run a current across this coil, and that focuses your beam. Okay? Important details here are that literally anything that happens to this can affect how it interacts with the beam. So over time, let's say that we build our electron microscope. Nobody's typically going in and on an ordinary Tuesday touching these things, but let's imagine a little bit of dust comes off. Well, if a little bit of dust gets on here, or a little bit of stuff vaporizes and precipitates on here, then that will affect the magnetic field generated at this spot. You will need a way to adjust for that in a second. So when these are working properly, we apply a magnetic field. Our electron beam comes through this. The beam will then focus at a certain depth. And as you're adjusting things like focus level, you're adjusting this magnetic field. Because as you adjust the intensity of this magnetic field, you will focus the electrons in a spot that moves up or down. And one other detail here. This spot right here we call the aperture. In our electron microscope, the aperture sets the current. Current is how many electrons are heading down to your sample per unit time. More current, more electrons are hitting your sample per unit time. You're going to get a greater reaction for whatever it is you're doing. Close the aperture down, you limit your current. Open the aperture up, and you increase your current. So on our SEM, the specific setting that will control beam current is the aperture. This is one of the tools you get to select on an electron microscope, which is the current. We will also see that you get to set accelerating voltage. There'll be important reasons for doing that. And as you're going through and focusing an electron beam to get onto your sample, you'll be adjusting a few other parameters to correct for whatever else is happening in the microscope over time. There are a couple of things that happen in an electron microscope as contamination builds up on these magnets. They are a couple of types of aberration. These are the optical versions of these. If you've ever heard of spherical aberration, this is what happened to the Hubble telescope when it was first constructed. The mirror was ground slightly off, and that led to fuzzy images at first. They had to put lenses on the telescope to correct it to get it to work. That can happen in an electron microscope as well. If your lens is not focusing every part of the electron beam at the same vertical level, then you're not going to get a crisp image. Chromatic aberration in a lens is different colors get split out and different colors focus at a different level. In an electron microscope, rather than this being a glass lens, it's magnets once again, but the electrons that come through the set of magnets coming through with slightly different energies. If one comes through with an energy of 14.9 kilovolts and one comes through with 15.1, make a good image, you still want them to focus at the same spot. But two electrons with different energies moving in a magnetic field move slightly differently. Chromatic aberration would be as a function of energy. Electrons are being focused at different levels. Most electron microscopes will include some set of additional magnets that allow you to correct for the development of various aberrations over time. These can be digital tools also. Here's an example of the lens being turned off. Here's an example of it being turned on in electron microscope images. All it does is correct for buildup on those magnets over time that makes things iffy. Anybody got how many of us are wearing glasses? We got, anyone having astigmatism? Okay, so can electron microscopes. This is a misshapen beam. It is a non-uniform magnetic field. So if the magnetic field on one side versus another is not precise, it will lead to a beam that is slightly off-center, just like what's going through my eyes. This can be manufacturing defects, but this is one that very commonly shows up over time. That as your electron microscope gets more use on various things, contamination can build up on the magnets, and that can lead you to having to correct for this gradually over time. This is called a stigmator coil. Normal operation of an electron microprobe or microscope will require you to say, oh, the magnets are making this a little bit oval shaped. I need to correct for that by attaching an additional magnetic field to restore the original shape of the electron beam. Here is an astigmatic image where the electron beam has gotten a little bit out of focus. We adjust it with these additional magnets, and that takes the electron beam into a single circular beam and gives us a better image. Astigmatism can be recognized when you go out of focus, it stretches in a certain direction. That is usually the way you recognize that you need to correct for this. That as you are adjusting this, you are trying to shape this beam down to that shape. You are turning magnets on and changing the intensity to try to bring it back to this rounded shape. So ideally speaking, when you have corrected for this, the trick on this one is you take it a little bit out of focus. If it's out of focus in this shape, it just goes out of focus all in the same direction. If it's going out of focus and bending in a certain direction, and you see it, that there's a preferred direction that it's going out of focus in, that's the hint that you need to adjust the stigmator coil. On ours, it's forgiving enough that this setting does exist, but we typically don't have to adjust it. That is not the case on every electron microscope I've used. And I would say that getting this right is one of the more complicated things to have to figure out on an electron microscope. Because you're not just having to focus, you're having to focus and then go out of focus, adjust the direction in which it's out of focus, and then bring it back into focus.
Is a automatic setting for stigmatism. We also have autofocus, and considering my glasses here, autofocus works better than my eyes at trying to focus the image. And the same thing applies to our auto stigmate adjustment. You can go in there and I'll show you how it works. If you just hit auto stigmator and you're looking at something that you're pretty sure is supposed to be round at high magnification and it doesn't look round, the auto stigmator does a really good job of improving it. You can also try to do it manually, and fortunately you can do it manually. I can't do it any better than auto, and you can mess it up really bad and fortunately not save it. So or you could just do auto stigmate to get it back. So in several ways, the auto setting is very forgiving on this kind of instrument. And Brian's right, doing it manually on, say, a field emission instrument is an art.
Yeah, there's some things I will say we just have to practice, but at least you're going to leave here knowing what these are, so that if you're on a field emission gun and someone tells you, oh yeah, you just adjust the stigmator, you at least know what you're trying to get.
I would say that stigmating our images is a lot easier than getting a carbon code out of our carbon.
That is fair. But that's our building, and we have a desktop SEM, not a field emission gun. Okay. Mentioned these earlier. Okay. Two things that you will get to set on our SEM are current and accelerating voltage. Current is how many electrons are coming down per unit time. Accelerating voltage is how hard we're throwing the electrons at the sample. It is the energy that they're getting fired at the sample with. These two additional properties are settings that you will get to control on every SEM or electron microprobe that you ever work with. And they affect how the SEM interacts with the sample that you're on, and how it generates images and responses in the sample. All right, whole text slide. Stuff to think through in terms of your settings. The highest precision that I have found that has been reported for a tungsten filament is a spot size of roughly 10 nanometers, which means that if you're taking a 1024 by 1024 image and your spot size is 10 nanometers, you're basically able to focus down to about a 1 micrometer spot size as the best possible image with a tungsten filament. Doesn't give you a very strong signal because you're at a single area, but that's the best that's reportable for that. A field emission gun, where you have that super precise tip, can shrink the beam down by a factor of 10 compared to that. That can give you, in a scanning electron microscope, some ability to get a sub-micrometer scale image and actually keep everything in focus. It's doable on the right SEM. What then are your trade-offs? Well, the more I turn up the current, the more my beam is going to spread out. So if I'm analyzing a very, very small area, I want a very, very small current to control how much energy is hitting that spot. Increase the current and the beam becomes larger. This will limit the size of the object that can be imaged, but this will improve my image quality because a higher current will produce a stronger response from the sample that I'm analyzing. That's an example of a trade-off. If I want to get down to the smallest possible analyzable area and zoom in as much as I can, I might need to minimize the current. But if I want to produce a strong response that makes very fine scale features pop out and show up in my images, I will want a higher current. Same thing in accelerating voltage. Low voltage will cause the beam to spread out a little bit more. High voltage will limit this because the higher the energy is, the more the magnets are going to respond to the electrons coming through. In low voltage, the beam will only penetrate a little bit into the material. At high voltage, the beam will penetrate more. This can help with fine scale observation, but this could help with getting a broader image with a larger depth of focus. You'll see as the week goes on in my various class versions of this, that there's a number of spots where while you're doing SEM analysis, you have to think actively about what you're doing. What is the signal that I want to get out? What analysis do I want to get out today or in this batch? And the answer may change as you're doing one analysis type to another. You may want more than one analysis type on a different sample. Another factor is going to be working distance. We'll talk about this in a little bit. This is going to be how close your sample is to the electron gun. If I want a broader field, I move my sample down and it spreads out the focal area. If I want to focus on a single spot, I move my sample up close, and that gives me a much narrower spot. All of these things are adjustable, including in our electron microscope and in the big fancy ones that you might find in another room. All of these analyses are done under vacuum. As we start next thinking about how the beam interacts with the sample, we do want to pay attention to the fact that everything's under vacuum. There's a couple of different pump varieties. Most vacuums will have a turbo pump. You'll hear this occasionally operating on the thing. It starts off with a roughing pump, and then this high-pitched pump will start up, and that's this spinning turbo pump that helps take things down to a very fine vacuum. So we're going to take a sample, we're going to put it into an electron microscope. at a pressure of about 10 to the minus 5 pascals. About 1 electron in 10,000 will collide with a gas atom as it's traveling through the column. If you increase the pressure in the gun or in the column, you will have more electrons hit gas molecules and interact with them. Fewer will hit your sample. Talk about why you might do that later. Every SEM is going to have some version of a boundary between the part that's under vacuum and the part that's the real world, where you have to undergo a sample exchange. Every SEM will have its own method for sample exchange. Ours is relatively simple. And in fact, ours is built to do that very, very quickly. This one is a much more expensive and fancy version of a sample exchange chamber on a field mission gun. These setups will often be, you load your sample, you close this, you pump this section down under vacuum, and then using this handle, you insert your sample into the SEM or microprobe while it remains under vacuum. These can be complicated. Anybody used one of these? No? Yeah, like this is one of those spots where if you're ever using a field emission SEM, it's one of the spots where you pay attention to the SEM operator. Because none of these are designed the same way. And if not done properly, this is one of those spots where you can actually break something. Because you're actually inserting your sample in under vacuum, so if you accidentally knock it off the track, you can't just get in there and pull it out by hand. So, yeah, ours, it'll be nice and simple. That is one of those things worth knowing. Okay. All that I've covered so far is logistics and design of the microscope itself. The next set of stuff is all the signals that are going to get produced on the sample. I'm going to pause for questions first, or for anybody to get up and grab coffee. Anybody want to take a restroom break? This is a good restroom break spot. I'll pause here for a couple of minutes. Everybody take a good break. Giving me a frowny face or just checking something out up there? Okay.
It is seemed like good, clear explanations. It seems like it got simpler.
I added two slides. I moved some stuff around, but I added I didn't have a good example of what the aberrations were of the spherical and chromatic aberration. So I added a slide discussing that.
That was a good slide. I like that.
Otherwise, for the most part, this one I didn't change too much because I knew we had a lot of debate last year over this one. So I worked mostly on the other ones. Yeah.
You took away. Never mind. You were upset at me last year because it made you take away the picture of saturating a tungsten filament.
What was that? Yeah.
I never did bother to explain to you that the reason I didn't like that slide was just because I thought it was a crummy slide showing how it really happens. When I envision it, I don't envision some wavy thing getting higher and higher. I really do envision a curve and flattening out. And I'm not even sure what's on the X or Y axis of my vision, but it corresponds to what's happening when I'm turning the dial. Anything, they don't have to saturate it more.
Oh, there's a lot of things that still use them. So.
There's a new kind of filament I can think of the name. It's some kind of tungsten, which is not in the least bit like the traditional tungsten. Instruments like the ChemiSem, the Thermo Fisher ChemiSem, have it, and it's absolutely impossible to look on Thermo Fisher website and find out what kind of filament they have, because it's somehow very proprietary. I somehow dug up the name of the type of filament it was. I asked them about it, and they looked at me like, "How do you know that word?" Yeah, I don't know it anymore. I completely got it. I By the way, PM stands for preventive maintenance. The thing that like a guy wants.
Oh, yeah.
I think you should.
Then they're going to bill us differently. Preventative maintenance is what's already paid for. Yep, that's why we have the spare ones. I'll even take them out of the room if I have to. Okay, that's everybody other than Willie. Everybody have a good break. Okay. Okay, so we've covered thus far just the mechanics of what an SEM is and kind of what it's trying to do when we're creating a beam. The next section is I put a sample in. What actually happens in my sample when I hit a piece of material with an electron beam? I do a whole bunch of different things. And there's, what do we have? 6 different responses listed here. And there's other ones that you can certainly come up with if you're being creative. So there's a lot of different things that happen when an electron beam hits a sample. Even if it's just at low voltage, when electrons come in and hit a sample, it doesn't just stop at the upper layer of atoms. The electron beam will penetrate into the sample and produce a variety of interactions in an active volume beneath the electron beam. And every one of those reactions, everything that the electrons are doing in this sample can produce a measurable signal that you may want to analyze for some purpose. Some of these are very specialized, and you have to buy an SEM specific. By the way, are you trying to take a photo of this one? On that USB stick, all of these are already loaded for you. So that is one of the reasons why you have a USB stick. I did not mention that earlier. So yes, you have all of these presentations already loaded on your USB stick for archiving. But yes, you get to keep that. No reason to. It's not that photographs aren't allowed; it's that you don't need to. Got it. All right. So our SEM is going to do the most common setup of these, which is 3 of them. SE2 or secondary electrons, backscattered electrons, and characteristic X-ray analysis. The other ones, there are tools that can do pretty much all of those. You may have to buy an SEM that's designed to do it. Cathodoluminescence, OJ, if I'm pronouncing it correctly, electrons. Those are things you can build an SEM to do, but you have to build an SEM to do them. Oh, yeah, it's probably a typo. Blame the paper, the 2019 paper. BSE. I'd say BSE. Almost everybody calls them BSE. All right, so let's go through the key ones, the key responses that you should actually know what they're doing when you walk over to our SEM. Number one on the list, perhaps my favorite. Yeah, this is my favorite, is backscattered electrons. Probably most of the imaging I've done on SEM is backscattered electrons. What happens in backscatter is an electron comes in, keeps its energy, interacts with an atom, whips around the atom without losing much energy, and gets shot back out. So electrons enter the outer layer of a sample, bend around a nucleus, and head back out. Because this is related to electrons interacting with an atomic nucleus, it is a function of charge on the nucleus, squared, for various reasons I'm not going to derive. BSE imaging is basically, therefore, a signal produced by the average atomic number of your material. The higher the atomic number is of a material, the stronger the response will be. Brighter things in a backscattered image have higher atomic number. That is the rule of thumb here. In this image, I believe this is one of mine. Yeah, this is actually one of mine. Taken from, Serena has this sample actually right now. Yeah. We have a couple of different phases. In the background, we have a feldspar. Calcium, aluminum, silicon, and oxygen. All of which are near the top of the periodic table. Nothing is in the middle. All of them are fairly light elements, so they're giving us a weaker response. Aluminum, magnesium, and iron, silicon. The one that matters there is the iron. Iron is much lower on the periodic table, has a much higher Z number, gives us a stronger response. But it's still iron and silicon with some magnesium. Here is an iron oxide, and here is an iron sulfide. The iron sulfide is the brightest thing here because the average Z number of the iron is higher than anything else in this image, and the sulfur has a higher average atomic number than the oxygen next to it. So the oxide is almost as bright as the sulfide, but not quite, because the Z number of the oxygen is lower. When you get a backscatter signal, you are literally looking at an expression of the Z number on average of the material under electron bombardment. Now, in backscatter, there is a strong dependence of scattering behavior on the angle of the surface. So if I have a nicely flattened surface and I do a backscatter shot on it, the electrons come down, whip around the sample, and come back up in the direction of my gun. The highest flux in this case is along the beam direction. But there is a very strong slope effect. If my material is not perfect, if my material is not flat, then I will send my beam down, my electrons will whip in, and they will head off in some unknown direction, depending on the surface angle. Backscatter imaging will still work on material that is not flat. Powdered material, rough material, whatever it is, you can still get a backscatter signal out. However, you will also be getting a signal associated with topography. Because if my sample is rough, some fraction of my electrons do not make it back to my detector position. Secondary electrons are going to be the one that works for sample roughness. This is a very different type of electronic interaction. In a secondary electron, I send an electron at my sample. It hits my sample and knocks off an outer electron. So we are producing a secondary electron because it's literally the primary one's the one I shot, the secondary one's the one that came out. So if we think of, we do the pool metaphor. This is the cue ball coming in. The secondary electron are the electrons that scatter out as it hits the other balls. Secondary electrons, unlike backscattered electrons where there's a main direction perpendicular to the surface, these will head out in all directions. So we have our atom, we start generating secondary electrons, they scatter in all directions. These are somewhat lower in energy than backscattered electrons. So they will get absorbed by other atoms surrounding them, unless there is a surface where it can escape from. So for secondary electrons, if we fire our electron down here, it goes into the sample, some amount come out that way, some amount go into the sample here. If there is an edge, though, we get a higher flux of secondary electrons coming out of our edge. There's a cosine built into the math here somewhere as well. So for a secondary electron, in this case, the amount of electrons we get out is a function of the orientation of the surface. And unlike backscatter, we don't get the biggest flux of secondary electrons if it's flat. We instead get a bigger flux of secondary electrons coming out of edges. So let's take a look at a secondary electron image. And I found a NASA one, so we're going to use a NASA one. Little crystals of stuff. What do we see when we look at this in secondary electrons? What's the brightest part of this crystal? Edge. Why? Because this material is under electron bombardment. The electrons are escaping into the sample, but then they're concentrating and coming out the edge because it hits the edge of the material. Look at the crystals on the surface. They pop out in secondary electrons because the edges are the things that brighten up out of this. Small bits on this, little things that protrude, they tend to show up as brighter in secondary electron imaging because instead of it backscattering straight at my detector, it's spreading out in the sample and then escaping out the edges, making the edges of things the spot that stands out. You look at this crystal in the back of whatever this is along the edge of the bug, you get a very good view of this. Where we're seeing the high secondary electron signals, it's coming out of the edge because that's the shortest path length and that's the highest fraction of electrons that we get out with those energies. Okay. Two types of images here. One is a secondary electron image. One is a backscattered image. Which is which? I assume I'm deaf. SE and BSE, that is correct. And the one at the top, the secondary electron image, You're seeing particles on the surface. You're seeing the edges of the material come out. In the bottom, you're seeing, is there any Z number contrast? In this material, there really isn't. Presumably what it's a zirconium aluminum alloy that I found the image of here. Same game. I think I got this one from Serena. Which one is which? This one is backscattered electron. This one is secondary electron imaging. What can we see? Well, in the backscattered electron, we're getting a high contrast, excuse me, between phases that are iron rich or whatever else it's probably iron, right? Iron sulfides again, and the oxides, okay? They do still stand out in secondary electron imaging because we're still able to get a slightly different response in them. Here's a bug or a void. In backscatter, we're sending electrons into this. They're going into this bug. They're not reflecting back to our detector. So this basically just has gone dark. In secondary electron imaging, we're getting a signal out of all this that we can detect. So it actually shows, and we can see the texture of this little vesicular vuggy area in there because it's being done in secondary electron imaging. Okay, so compositional contrast imaging in backscatter to recognize phases. Secondary electron, we're seeing spots on the surface. We're seeing textural differences. This is on a clay-rich material, again, done on SEM, I believe. Which is which? Correct. BSE, it's all clay here, so there's not a lot of contrast between them. Okay. What do we see showing up bright in this one? All the edges. Why are all the edges bright? This is a secondary electron image. It's illustrating the topography. It's illustrating the surface features. It's illustrating the edges. You're not. This is why I wear the N95 on, because I'm asthmatic up here who's half dead up there sometimes. All right. You're not going to see this on our electron microscope because it's locked inside a tube and not accessible. This is what the sample chamber often looks like with your sample and these two detectors and the electron gun. On a field emission device where you have the whole thing that opens up, you may actually see all of these. And it may be incumbent on you to avoid bumping one thing with your sample, which is one of those things that can happen. That's not a worry on ours. Here is the secondary electron detector, and here's the backscatter detector. Okay? So the backscatter detector is literally placed often right beneath the gun so that electrons that hit the sample and scatter back give you the strongest signal. Has a little hole in it to let the electron beam through, and that's it. The secondary electron detector is off to the side because it detects lower energy electrons. The secondary electrons have lower energy. The backscattered electrons have higher energy. They basically have the energy they come in with. So the setup is the secondary electrons are images taken by electrons coming off to the side. Backscattered electrons shoot straight up at your detector, and that's the position of both of those. Oh, these are called Everhart Thornley detectors. I'll talk more about those if we get to the advanced section on Thursday or Friday. Here is a backscatter detector. Here's our secondary electron detector off to the side. It has a hole in it to allow the electron beam to shoot through it, and then it absorbs everything that's coming back up. These are thin. They are sometimes actually removable, so that if you don't need a backscattered image, you just get this out of the way. It's broad, so it will collect signal over a pretty large range. And you want this in the as close to in the path of the gun as you can, because the strongest backscatter signal on a polished sample is coming straight back up at you. If we're taking a high quality BSE image, the reason we're doing this is that we want to recognize what is different about one material versus another. One phase versus another, one compound versus another, something like that. So we put our detector almost in the path of the beam so that we get the strongest signal coming back up. And the response in that case is effectively a look at the average Z number of the material. So in the image we saw earlier, you're looking at highest BSE return in the highest highest Z number materials. And then you get to play with contrast. You get some response that is a certain number of electrons coming back over this area. Well then, do I want to adjust the contrast to see all of the materials that are in there? Or do I want to narrow it down to a certain band and do a digital processing on that? That will be in the image processing here. So if I want to, I can use contrast to bring out the difference between plagioclase and orthopyroxene here, both of which are pretty dark. That I can adjust the contrast to be able to see. If I do that, to focus in on the difference between these 2 or 3 phases, I'm going to wash out everything that's higher Z number. If I want to see differences between all the things at high Z number, I may blend together all the things at low Z number. So image processing is what you're going to be doing when you adjust a contrast dial. And that is allowing you to focus in on a certain range of electrical responses. So to do a good high quality backscattered image, you need to first focus the beam on your sample, set your brightness and contrast based on the phases that you want to distinguish. Do you want to distinguish high Z number elements from high Z number elements and wash out all the stuff that's darker? Or do you want to focus in on the low Z number elements and be able to distinguish K feldspar from quartz and leave all the high mass elements washed out? Those are the choices you have to make as you're setting your settings. That means you have to think through what is it you want to see in your sample. If you're trying to identify zircon grains, you may use one contrast band for that. If you're trying to identify olivines and pyroxenes, you may use a different contrast band for that. Here is another example of that. This is using contrast to bring out the features of interest. So here, we have a big, broad contrast zone. We kind of zoomed in on this one. Here we've included some of the area in the background to bring out a better image of this particular material. Adjusting contrast is going to be something you're going to have to deal with. Most SEMs, including ours, have some sort of setting that allows you to turn on and mix your detectors. Ours has 2, I believe they're called topo settings. On a field emission gun, you can often adjust exactly how much fraction of each image you want to get, so you can combine a secondary electron and backscattered image. This is a solar cell. I found an image comparing all 3 of those here. On the left is silver and the right is silicon. So in the backscattered image, the silver is a lot brighter, but you can see the edges of the silicon crystals popping out here. in the secondary electron image. So when you do a combined image, what do you get? You get the edges of the silicon crystal still popping out, as well as the compositional difference between the two. There's no formula for how to get this to work best on any particular mineral. It's one of those things you kind of play with if you have an odd material and you want to be able to see combination of textures. Topographic imaging might be, I think it's probably safe to say, this is the most common use of the SEM. It takes advantage of secondary electrons or a combined signal and lets you see things that have some shape to them, whether that's a fossil, whether that's a cell, whether that's some metallic thing that you've made. Because the secondary electron detector is off to the side, the orientation of, as if you turn your sample, will always get a slightly different image. So it is possible to make sure, it's possible to get a very good image by playing with a combination of moving your sample around and changing all the settings. So what all have we had to go through here to get to an image like this? We have to set the kind of image we want. We have to set the material we want. We have to set the focus. We have to set the current. We have to set the accelerating voltage. And it might even be we have to play with how we want to orient our sample to get our best image here. There's a lot of things you're going to have to manipulate to get a particularly good image. Understanding where most of them are coming from has been part of this whole exercise. Now we come back to mentioning depth of field, because in that last image, you're seeing something with a good depth of field. This is a set of fossils stacked vertically there from the USGS lab in Denver. This is associated with where we put our sample relative to our gun. In an electron microscope, there is a specific plane where things are truly in focus. And then there is always going to be some area around it where things are good enough. That good enough is depth of field. So you can see things that have 3D quality to them in many SEM images because there's a broad focal zone. For the best quality image on a single surface, bringing the focal plane up and having a very small depth of field is ideal, because if I want to image my flat surface, I bring my sample up close to the detector and focus it at that level. If I want to get an image that has verticality to it, that has a depth of field to it, I move my sample further down, and that spreads out the focal zone so that I can get more material and more volume in this area. This on most SEMs is called the working distance. A shallow working distance is bring the sample up close to your detector. For imaging on a flat surface, this will give you the highest quality image. If I move my sample down, that is useful for looking at stuff that has topography to it. Aperture size, or in other words, current, will also play a role here. Smaller aperture sizes leads to a larger depth of field because it kind of cranks these two green lines closer to each other. So you get a bigger, broader zone where it's still in focus. We cannot do this on our SEM. And in fact, it was difficult to find a good image of this. It is possible on an SEM, including some digital tools today, to set an analysis where it will scan vertically and that it will adjust its focus level, take a picture, 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 and get a truly 3D image. I don't even think the Johnson Space Center ones are built to do this. This is one of those things that would be in advanced operation that would be cool. We don't do this one here. It is possible with the appropriate software to make this happen. This is on some sort of a cellular structure, and obviously you're in a geology building. I have no idea what the NIH was doing here. If you want to check out the reference, you can check out the reference. Okay. But one thing that we can do here, and often do, is map things out horizontally. So instead of stacking vertically to try to change the depth of field, horizontal image stitching is a very useful technique. Because if I want to get a high resolution image over a small area, I can take a single frame. What if I want a high resolution map of my entire sample? I can't do this with a single focus, so I have to trade off. Do I do a bigger spot and lose my detail? Well, the way to handle that is digital image stitching. Each one of these is some version of a set of images that have been stitched together. On some of them, you can see the image stitching boundaries. On some of them, the stitching is ideal enough that you actually can't. Which is pretty good to get to. So we have cells, we have rat brain cells. Rat brain cells number 6. That's what I get when I steal images from the NIH. Horizontal image stitching can take time and can require you to produce some fairly high file size images. This is a common way to get high resolution maps over a big broad area. That way you don't have to spread your beam out, you don't have to zoom out. You take a very fine scale observation and stitch them together digitally. Other settings you will be having to deal with include brightness and contrast. When you're doing this, there is always some noise in an electron microscope, whether it's from sample vibrations or statistical fluctuations or electrons bouncing around. There's what's called the Rose criterion, a technical definition of a good signal to noise is your signal is at least 5 times what the noise is. How do you get a good signal? If you're not getting a signal, you have techniques you can do to get this. Increasing the beam current, increasing the aperture size, slower scans, so that you acquire more data. The noise will kind of cancel itself out. A longer scan will give you more data. Larger sample areas. If you're too tightly packed on a single area, the noise is going to be a significant portion of your signal. Zoom out a little bit. That can give you a better overall signal. And making sure everything is calibrated as well will matter there. And then the other thing to manage signal to noise is sample preparation. This afternoon, many of, or at least one of the 2 groups will spend time doing sample preparation with me. We're going to give a brief overview of it here, and then we'll let you play with that more later. Non-conductive materials under electron bombardment will build up their own electrical charge. And that buildup of electrical charge will affect further operations. It can lead to signal instabilities. It can lead to extra releases of electrons. It can lead to image distortion. These horizontal lines, the bright lines in this image, the section of this one that's glowing, this is additional electron release due to the buildup of charge in a sample. This one, where it just kind of looks stretched out, is the beam itself getting distorted as it interacts with the sample because the sample has started building up charge. How do we manage this? This is a cool image to find. I like this one. Here are gold-coated insects. Like that. I like this one. All right. If you have a non-conductive material like, I don't know, a cockroach, okay, how do I manage this? Well, I'm going to do what we call sputter coating, where we add a very thin conductive layer onto the surface of my material and use that very thin conductive layer to carry away the current. We then connect that material directly to the SEM with something that is conductive. That allows charge as it builds up to flow away, preventing me from getting any of those image distortions. There's lots of things you can coat stuff with. Gold is what's been done on the bugs there, I'm almost certain. Platinum coats, silver coats, all those things can be done. Many geologic samples, we use carbon. Because if we're not interested in carbon itself, that's a good conductor and it's fairly cheap to work with. Why would carbon coating not work well on a cockroach? Because it's carbon. This has been coated with gold because it's literally material that's made of carbon. We'll talk more about that later. Go for it. Don't forget your mic.
Section of a rock is that once you get the bug coated, you can't ever get the coat off. I mean, I suppose if you dropped it in something, it would dissolve the bug as well as the carbon coat or whatever kind of coat you put on it. But it's very typical that we put thin carbon coats on polished thin sections of rocks, like silicate minerals, which are not conductive. And then we can take the coat off very easily if it gets a little bit dirty or if we need to look at it optically without the coat on it. You can take it off and then you can recoat it. So that's the difference between a 3D thing and a polished sample.
Go for it. Yeah. So
No.
but you want to go?
Well, I was going to say, the whole thing needs to be conductive, and so you really need to have a conductive coat on the middle of the thing, not just a piece of carbon tape on the side. We use the carbon tape or a piece of aluminum tape or copper tape additionally in addition to the carbon coat to make sure we have a contact between the top of the sample with the carbon coat on it and then the middle of the holder itself.
And also to just hold the insect in place, because if it's just loosely on there, well, then a tiny vibration, I bumped into the table, that can cause it to shift a little bit. If I'm in the middle of collecting a long image of my little roach leg here and it's not attached, that little bit of motion can be enough to make my sample move mid-analysis.
Well, plus we don't want bugs in our SEM, bug pieces in our SEM.
Yeah, I was just going to follow up on what Serena said. And put things without in the SEM. Your images will have some problem with them, but if you're just looking at something to get a rough idea of what it is to go on, can do that. It's not going to occur. I have done that. I would look at things before.
And that's specifically what we use a low vacuum setting for looking at things that don't have conductive coats on. What?
That was the next slide.
Sorry.
Previewed the next slide.
I'll just leave the room.
I kicked Serena out. Yeah, so there are techniques that we can use to image things that are not coded or to limit the charging effects on things that are not coded. They're not always perfect, but you imagine you want to image a cell, okay? It's going to be difficult for me to gold coat a single cell but I might very well want to image a red blood cell for various reasons, or skin cells, whatever. It can be challenging, very challenging to gold coat a single cell. And I might want to actually image something that's happening to it as it's in there. That could be imaging a chemical reaction. That could be imaging something that's going to dry out. If I don't pull a full vacuum in my SEM, I leave some additional gas in there. That gas can remove some of the charge. It will not necessarily remove it all, but it can remove some. Now, in my design for my electron microscope, I have to do something particular here, because if I'm going to leave my stage at an elevated gas pressure, I can't have that gas pressure get all the way into my gun column, because the longer the gun column has more gas molecules in it, the more electrons get used up in the column. So typically to do this, there is some version of another aperture here that will limit gas flow upwards into the gun to make this work. Our SEM is considered an environmental or variable pressure SEM that can allow specific gases in to remove some of the charge. This is considered variable pressure mode or environmental SEM mode. So for this, when you know you have a material that is not coated and not perfectly conductive, you can plan ahead and say, we're going to let some gas into the sample chamber, and that gas will help remove some of that charge. It does affect the beam. This is another of those trade-offs. You cannot avoid this. It's like the metaphor I have for the beam here is it's like driving through fog. If you let gas into the chamber, it will stop some of the beam. It will deflect or spread out some of the beam. So variable pressure mode, you will not get the highest resolution possible. You are sacrificing some of your resolution in order to do this on a non-coated sample. Secondary electrons effectively cannot be measured in variable pressure mode. In fact, on our SEM, when you go to variable pressure mode, the secondary electron detector just turns off. You can't actually use it, because backscattered electrons come out with high energy. Secondary electrons come out with low energy. Secondary electrons with low energy hitting gas molecules just get absorbed. Backscattered electrons with high energy do shoot back up, and they're still detectable. So in this setup, you better be doing something you can analyze with backup. You can still get some topographic image. There's there's actually designs out there where if for some reason you need a secondary electron image of a material that you can actually map out the ionization of the gas in your chamber and use that as a way to get an image out of this. I have never used something that fancy, and I probably never will in my career. But I'm sure there's a biological SEM out there that can do this. There will also be an effect on X-rays emitted from the sample. No, we have not talked about X-rays yet. Migration of stuff through an SEM, including an environmental mode, is a factor that you may need to deal with. If you have a sample that's actively degassing during your analysis, you don't necessarily want all that getting pumped through your vacuum. You don't necessarily want that getting pumped through your column. If you're doing that in variable pressure mode, you're letting some degassing happen, and then some of that gas is actually entering the column because none of those apertures are perfect. There are SEMs where if they're built to do specific organic compounds, cold traps are put in to capture some of the vaporized organic stuff. Ours does not, so you get one slide on this. but here is an SEM that has a cold finger assembly right there next to the electron gun, so that as carbon or other organic compounds get vaporized by the gun, rather than that stuff coating everything, it coats first a cold spot where it's designed to precipitate out. All right. Yes, I do have that there. All right. So, as an overview here, when you get on our SEM this afternoon, the things you're going to need to do in order. Yes, this isn't a handout. Thank you. Are first, prepare sample. We have a whole section on sample prep later. As you're loading this, on ours, you have to set the working distance before you put stuff in. On others, you may have to set it afterwards. Ours, you have to set it before. The things you're then going to be able to adjust on ours include the vacuum level, the accelerating voltage, the beam current, which, as we said on ours, is the aperture, which detector you want to use, and then how long do you scan across a zone, and how much do you zoom in on a single zone. You can drive around, you can zoom in and out. As you do that, you will then need to actively be adjusting things like focus and brightness and contrast to keep the analysis working on whatever it is you're looking at. Brightness and contrast can even vary across a sample depending on how good your coding is and such. When you actually take an image, you're going to want to determine the image resolution. File size is a good one to save in here also. And also, on these types of images, do you want a data bar? Do you want a scale bar? Do you need something at the bottom saying what your file name is? Those are very common on there as well. In a second, we will talk about, as the last thing for the morning, EDS analysis or X-ray analysis. That is the last thing on the list for the morning. Those will be a different set of analyses. They can be done as spectra, line profiles, even quantitative analyses as well. And then on Friday, we will work with some combined image and X-ray data processing as well. That will take a couple of days to get to, but you'll see how to get those as we go. Questions on any of that so far before we switch topics slightly to our last detail? Serena, don't forget the mic.
Are you going to talk about adjusting working distance for doing ES analyses versus imaging?
Not necessarily right now.
Well, I might interject something.
That's fair. Anyone want to ask anything before we move on? All right. We have probably, what day is it? Wednesday into Thursday. I have a whole session set up for more details about this type of analysis. So we will go through this in much more detail later. But the last thing we want to cover before we turn you loose onto the SEM is X-ray analysis. This is another powerful tool of shooting electron beams at stuff. And this is the origin of an electron microprobe as well. This is an additional thing that happens under electron bombardment. So if you remember our images earlier of backscattered electrons zooming through, secondary electrons coming from the outer part here. The third type of interaction that we might analyze is an X-ray response. When we shoot high enough energy electrons at a sample, they can whip around and leave, they can knock off outer electrons, or they can knock off an innermost electron. if we knock off one of these innermost electrons, we now have a hole in the electron cloud in our atom. An outer electron will fall down from one of the orbitals outside it to take its place. An electron falling from a high orbital to a low orbital will release an X-ray. So, electron bombardment of a sample causes release of X-rays. There is, we'll talk about this later, a broad spectrum of X-rays that's released from material as electrons whip through them. But then, some of them do the Planck thing. In other words, they make specific jumps where they are quantized so that if an electron falls down from this orbital to this orbital, it releases an X-ray with a specific energy. And every time that shift happens in that atom, it will release an X-ray with that exact same energy. Because the electron cloud will respond to the charge of the nucleus and the rest of the cloud around it, this X-ray has a characteristic energy for each atom. We call them characteristic X-rays. So, as we shoot electrons at our solid sample in a single spot, we begin generating characteristic X-rays that are X-rays with a specific energy generated and shot off from our sample. Here is a spectrum of X-rays taken by an energy dispersive spectrometer on an unknown material. EDS, energy dispersive spectroscopy, is the X-ray detector built into many electron microscopes. They're super useful because we talked earlier about how EDS can give a relative, this is brighter than this, or BSE, excuse me, BSE imaging can give, this is brighter than this, and that's a probe of the Z number. This can actually tell me what something is made of. So here is on an unknown material. We fire energy at that. This broad background here that you can see here, this is a broad spectrum of X-rays being released by all the materials in the sample because electrons are going off in all sorts of directions and generating a lot of energy inside them. But then we get X-ray release with a certain energy characteristic of the atoms that are in our material. Our material here has a little bit of silicon, some calcium, a lot of iron, and a lot of oxygen. There's a carbon peak. In other words, this sample could have carbon in it, or most likely it's been carbon coated to create a conductive source. If we saw a gold peak here and we weren't expecting it to be something that had gold in it, but we gold coated our sample, it will show up here. So we may have to adjust for that in data processing. Recognizing peaks. Once it tells you the energy, you can actually do this almost by eye. If you know where to look on here, you can even recognize phases by the ratios between these peaks just by looking at them. You won't even have to do any math. It can be quick enough on that. There is plenty of data processing software built to work with these types of analyses. The groups today will focus on mostly dealing with group 1 today will focus mostly on image acquisition, image processing, and such like that in the afternoon. Group 2 with me will work on sample preparation and different types of sample prep and how to think through sample prep and all sorts of questions like that. Then we'll switch and do the opposite things in the morning. And then tomorrow afternoon, I'll go through the basics of EDS analyses in more than 2 slides, as well as how to look at and deal with some of the data. And then tomorrow afternoon, Serena will start collecting EDS analyses with you folks on some of these samples. And then towards the end of the week on Friday, once we've done EDS analyses on both spots and mapping, we will start putting those together with image processing to actually map out where material is and different phases on surfaces. Anything else you want to add right now, Serena?
Well, I just want to say something about working. Explained earlier that working distance, which is basically the distance between the final focal point of the beam and the sample. He explained why you might want to have short working distance for a flat sample and then a large working distance for a 3D sample to give you more depth of field. There's also another reason for having different working distances, and that's because of the geometry of how detectors are in most columns. You need to have, for EDS analyses, in order to collect the X-rays, you need to have a large working distance. So if your main interest in putting the sample is just imaging, you just want to get really good images on a flat sample, you would have a short working distance. But for the same sample, if you need to collect X-ray maps and X-ray point analyses, you need to have a larger working distance. And that's where there is a disadvantage in our SEM, because to change working distance, you have to take the sample back out of the machine and physically lower it on the stage and then put it back in. So it's a good idea to know what you're going to do first when you set the working distance before you put it into the machine. And the machine's smart. It'll tell you if you put it in with a low working, really short working distance, and you try to take an EDS analysis, it'll tell you. It'll say not at optimal working distance.
Go for it, Willie.
Can't hear you, Willie. Sorry.
Just say the two of you have been using the SEM considerably longer than I have, and as a relatively new user, you'll learn this when we get on the SEM, and that's why this workshop is structured this way. You just kind of have to play with things. Your good images. You're not going to get your first image. So we'll all have time to play. It's less about theory and it's less about the settings will not be the same. Play around with it.
Play is the optimal word because it's really fun.
There's no one optimal.
So yeah, in terms of thinking about working distances, this is a good shot of that. I think that's still a secondary electron detector in there, but many of the detectors, including the EDS detector, are placed off to the side. And so why does the working distance matter for that? Because if the X-rays are coming off at a certain angle, if my sample is too low, the X-rays don't hit the detector. If my sample is too close to the gun, the X-rays bounce off the gun themselves and don't get to my detector there. All right, so the rest of the stuff in this presentation, which I'm not going to go through this morning, you can do later if you want to. You have these presentations loaded. These are from the manufacturer of the SEM and the software coding company of the SEM. They have a whole YouTube page featuring things like how to optimize images in a Phenom desktop SEM. How to, what's the next one here? Are we going to advance? How to optimize images, part 2, electron beam settings, okay? Detector options, okay? What's all the stuff we just went through? This, what are you going to be playing with this afternoon? Beam options, how to optimize an image, detector options, and so on. they go through the same stuff here as a secondary resource. If you want to review some of the stuff we went through this morning while you're in the middle of that, you may certainly view those later, although there will not be a quiz, so it is not required. And that is everything else that is in the morning presentation. All right. So if you two want, so it is currently 11:20. If you two want to do anything for the next 30 minutes or so, you can. If you want to send people off to lunch early, you could do that. I'm game either way.
We have to make the groups.
Yes.
A very important thing is to divide you into two groups. And the best criteria for starting out is anyone that has to prepare samples that they want to look at should be in Brian's group. And anyone who has samples already prepared, are they carbon coded? Oh, okay. And if doesn't have samples to prepare or has samples already prepared should be in my group. But on the other hand, they have to be roughly equal. I mean, which is to say 5 and 4.
Okay, so so you two can be in the group stuck with me this afternoon. Who has something that they brought with that they want to work with? Is it just Kim? Okay, what state is yours in? Guess is you don't want these coded by anything, right? So these may be a variable pressure kind of thing. She already has them on tabs. Let's put her in, let's have her start off with the group that's on the SEM this afternoon. And that way, if it turns out that we're having a lot of difficulty getting even an image of this, we can then go into this in the sample prep and think through that in the morning.
Okay.
I like plan. Okay, anybody else? Anybody else bring anything with them?
One's gold coded, the rest of them aren't coded at all.
Aren't coded at all.
So,
Okay.
yeah.
Well, then that would be by the same argument that he just made.
Yeah.
You should start in the SEM group. Yeah. In my group. Okay, so now we've got only 2 that have to be in Brian's
And
group.
what was your name in the back?
So,
Okay, in my group, we have Kim.
MYA. Thank you. Did I get it?
it's
Thank you. Okay. Hey, who were our, thank you. I knew it was an initial, and I could not remember what it was.
And,
Missing victim,
I've forgotten her name.
yeah,
I think it was the person Chinese name.
yeah, I'm sure I'm sure I don't remember it.
Last name Chen, Ruiyan,
You have a spelling of that?
RUI dash LIN Chang. Easy to remember, she's Cornell.
Okay, and that means we have 5 of you we have to distribute amongst 2 groups. Serena, do you want 5 on the SEM this afternoon?
Well, we're gonna, considering that we have 2 low vacuum ones, which are,
Let's-
require
yeah,
extra
okay.
time. Let's have 4 this afternoon.
Okay,
how
so
about-
can we get 2 people who want to start with on the SEM group this afternoon? I'll take volunteers. This should not matter that much.
I'm gonna pick Tara. And who? Right, okay.
And
So
did you
how
say you
about-
get Tara also, Serena?
Tara and Nina. So I can remember to tell Tara about the address of Minoptic.
All right, so who all do I have?
Julia.
And
AIPA.
you're a famous musical opera.
Aida, is that how you pronounce it? Okay.
Okay, so this afternoon, the 5 of you will probably start with me in here. The other 4 of you will start with Serena over by the electron microscope. Anything you want to do otherwise this morning, Serena?
No, but 11:30 to 1:30 is 2 hours. So the question is, do you all want 2 hours for lunch, or would you like to maybe start the afternoon session at 1?
That works. Good, sure.
Everybody agree with that? Okay, that'll give more hands-on time, which is, all right. So we'll do that.
Also, if